Welcome all. In the last few lectures, we were discussing Hurwitz criteria and some numerical problems on it. And we will continue our discussion with some more numerical problems. By far now, we have discussed Hurwitz criteria. To check for a given polynomial whether the given polynomial is Hurwitz or not, we need to check two conditions. Condition number one says that all the coefficients of the given polynomial must be positive and non-zero between the higher order and the lower order terms. And the second condition was to check for the positive coefficients of continued fraction expansion of even to odd parts या फिर odd to even parts. What happens if any of the two conditions fails? With the failure of these two conditions, we directly concluded that the given polynomial was not Hurwitz. But what happens if any of the two conditions does not hold? Does not hold means any of the two conditions does not apply. Let me throw some light on it. Suppose if we are provided with a polynomial, say we are provided with s cube plus 7s, like this. We are provided with this polynomial. Over here we can see all the coefficients are positive, but some terms are missing. Over here we have the highest degree as 3, lowest degree as 1, so we are missing with the coefficient of or with the term of s square. But we can clearly see these all are the odd power terms. So the condition number one cannot hold if all the terms are odd power terms or the even power terms. Let me consider another example. Say we have s raised to power 6 plus 7s raised to power 4 plus 3s square plus 9. Over here we have all the even power terms, but also we have s raised to power 5 missing, we have s raised to power 3 missing, we have s power missing. But we can clearly see this particular polynomial has all the even power terms, so this means the condition number one will not hold here. In these two cases, the condition number one does not hold. Similarly, we have in the last lecture we discussed the abrupt termination of continued fraction expansion, and in that case too we could not derive any inference from the continued fraction expansions, so that in that case also the condition number 2 will not hold. So what to do in these cases? That is, in the cases where all the terms are either odd or even, or the continued fraction expansion terminates abruptly. Let us revisit the properties of Hurwitz polynomial. There were 4 properties of Hurwitz polynomial. The first one said the coefficient of s terms must be positive and non-zero. The second said the continued fraction expansion of even to odd or odd to even part of ps must give only positive quotients. Now we were discussing if these two conditions does not hold. If any of the condition or these two conditions does not hold, then we need to consider the condition number 3 and 4. If the condition number 1 does not hold, that means the polynomial must be either the odd polynomial or even polynomial. In that case, we will consider the condition number 3. If the condition number 1 fails, we will consider the condition number 3. The condition number 3 said the continued fraction expansion of ps and its derivative p dash s must give only positive quotients. That means for the case when the given polynomial is either odd or even, we will calculate its derivative, and then the continued fraction expansion will be carried forward with PS and its derivative, and its continued fraction expansion must also give only the positive coefficients. If all the coefficients quotients are positive, then we would say the given polynomial is Hurwitz. Similarly, if the second condition does not hold, that is with the abrupt termination, in the last lecture we discussed, with the abrupt termination means that any of the divisor will be the factor of the given polynomial. So in that case we will jump to check the condition number 4, which says the product of PS with any even factor yields another Hurwitz polynomial. In that case we will jump to condition number 4. This says if, say, PS is the given polynomial and we are required to check whether the given polynomial is a Hurwitz polynomial or not, and the continued fraction expansion of this polynomial terminates abruptly, it would mean that there would exist a factor P dash S which would divide this PS completely, and it would mean I could write this as P1S into P2S. So to prove this to be a Hurwitz polynomial, I need to prove that the product of these two polynomials that these two polynomials separately are Hurwitz. That is, this one is Hurwitz separately and this one is also Hurwitz separately. Getting? That is, the product of PS with any even factor yields another Hurwitz polynomial, or in other sense I could state that the product of two Hurwitz polynomial will yield another Hurwitz polynomial. So to prove PS to be Hurwitz, I need to prove that P1 is Hurwitz and P2 is also a Hurwitz polynomial. Okay, in the coming numericals we'll be using the condition number 3 and 4 to check out whether the given polynomial is Hurwitz or not. Let me state again what are Hurwitz polynomial. Hurwitz polynomial are those which have their roots lying only in the left half of the S-plane. They do not have anything lying into the right half of S-plane. Their poles do not lie in the right half of S-plane. In fact, all of their roots lie only in the left half of S-plane. Getting? Let us perform some numericals. If you remember, in the last lecture we performed a numerical with this PS, which was this polynomial, and it's the continued fraction expansion of even to odd part terminates abruptly. It means this given factor will this given polynomial will be a factor of given polynomial. That is I can write PS, that is the given polynomial, will be equal to S square plus 4S square plus 3 times of a certain other polynomial. That is, the product of these two will yield PS, and I need to check now whether this one is polynomial this one is a Hurwitz polynomial or not, and this one also. To check on these two polynomials whether they are Hurwitz or not, I need to know this polynomial also. Now this polynomial can be derived after I write this equation like PS divided by S raised to power 4 plus 4S square plus 3. That means this. Now I need to divide this PS with this to get P1 separately. Let us calculate this P1. Now we will be dividing S raised to power 4 plus 4S square plus 3 we will be using this as divisor. So this is the given polynomial. Now we will perform the simple division of this given polynomial with the factor s raised to power 4 plus 4s square plus 3. I'm performing the simple division, not the continued fraction expansion. Remember here. So to get 4s raised to power 6, I need to multiply this factor with 4s square. If I multiply this 4s square with this factor, I will get 4s raised to power 6. When I multiply 4s square with this 4s square, I will get 16s raised to power 4. So I will write it here plus 16s raised to power 4. With this plus 3, I will get plus 12 s square, and the other terms are 0. I can write other terms to be 0, plus 0 and plus 0. Now taking the difference, I should change the sign. After changing the sign and subtracting them, these two will cancel out. I will get 2s raised to power 5. Now minus s raised to power 4 plus 8s cube plus 4s square. Of this I will get plus 6s plus 3. Now I will continue the division. I need 2s raised to power 5 and I have s raised to power 4. So what can I do? I can multiply 2s with this to get 2s raised to power 5. So I will mark plus 2s here. So I will get 2s raised to power 5, that is multiplying 2s with s raised to power 4. I will get 2s raised to power 5. Then multiplying 2s with 4s square, I will get 8s cube plus 8s cube, and similarly multiplying 2s with this 3, I will get plus 6s, and the remaining will be 0. Again changing the sign and taking the difference, this will cancel out. I will get minus s raised to power 4. This should not be minus. Let me check. Over here we got this 17s raised to power 4 plus minus 16s square. So I will get plus s raised to power 4. Okay, so this should be plus. Similarly, these two will cancel out, and the subtraction of these two will give plus 4s square. This will cancel out. I will get plus 3 from here. Now this is the remainder. Now I will continue the division. I need plus s raised to power 4. I have plus s raised to power 4 here. So I will multiply this with plus 1. After multiplying this with plus 1, I will write it here. S raised to power 4. 4s square into 1 is 4s square, and plus 3 into 1 is plus 3. Now after the sign change, I will see all these are cancelling out each other, and I am getting the division to be 0. This is not the continued fraction expansion, it is the simple division of two polynomials. I carried this out to calculate this quotient, because PS, we wrote PS to be equal to s raised to power 4 plus 4s square plus 3 into P1s. To prove this PS to be Hurwitz, we needed to calculate these two factors, and this factor can be calculated. P1s can be calculated by dividing PS with s raised to power 4 plus 4s square plus 3, and it come out to be 4s square plus 2s plus 1. Now that means I need to perform the Hurwitz criteria separately on this and this to prove that the PS is Hurwitz. So I will write PS now to be equal to the product of s raised to power 4 plus 4s square plus 3 and 4s square plus 2s plus 1. I will consider this to be say qs, and I will consider this to be p1s. Now I will prove that these two polynomials, that is qs and p1s, are Hurwitz. Only after proving them to be Hurwitz, I will say that ps is Hurwitz using the condition number 3. Now let us perform the Hurwitz analysis on qs and p1s. Now we have this qs and we need to prove whether it is Hurwitz or not. So as we can see, this qs is actually a even powered polynomial. That means it is an even polynomial. Now we cannot perform the continued fraction expansion simply. I need to calculate its derivative again. Using the condition number 4 we will prove it. So I will calculate q dash s, its derivative, and its derivative will be 4s cube plus 8s, like this, plus 3 will be 0. So now I will perform the continued fraction expansion with qs divided by q dash s, that is qs divided by q dash s. Let us perform it. Q dash s, we have 4s cube plus 8s, and we will divide it with. So now we will perform our continued fraction expansion with this. This is the derivative of this. I need s raised to power 4, but I have 4s cube. So what should be the coefficient here? I will divide s raised to power 4 with 4s cube, and I will get s by 4. That is, if I multiply s by 4 with this, I will get s raised to power 4. So the coefficient over here will be s raised to power s by 4. So I will get here s raised to power 4, and if I multiply this with this, I will get 2s. So there is no 2s over here, 2s square plus 2s square plus 0 I should write, changing the sign to subtract. In the remainder, these two will cancel out. I will get 2s square here plus 3. Now this is the remainder. As we are performing the continued fraction expansion, so we will consider this remainder as our new divisor, and the old divisor, which was 4s cube plus 8s, to be our new dividend. So I will write it here, 4s cube plus 8s. I need 4s cube, but I have 2s square. Let us divide it here separately. 4s cube divided by 2s square. I will get 2s. That is, if I multiply this 2s with this, I will get 4s cube. So I should write 4s cube here, and if I multiply this 2s with this, I will get 6s over here. Changing the sign, I will get 2s here. Now this is the remainder now. Now this remainder will become my next divisor, and the previous divisor will become the new dividend. So I will write 2s square plus 3 here. I need 2s square here. I have 2s only, so I will multiply it with s to get 2s square. I will get 2s square here plus 0, changing the sign. These two will cancel out. I will get 3 as a remainder. Now this remainder will now become my new divisor, and the old divisor will become my new dividend. That is, I write 2s here. To get 2s, I should multiply this with 2 by 3 s. So I will get 2s, and after solving, changing the sign, I will get 0 as the remainder. That is, there is no remainder. Now I need to check whether the continued fraction expansion has been completely terminated or the abruptly terminated. I will check it by checking the highest degree of the given polynomial, and the highest degree of the given polynomial was s raised to power 4. So that means the continued fraction expansion must have 4 steps. This is the step number 1. This is step number 2, or the division number 2. This is division number 3, and this is division number 4. That means I can say that continued fraction expansion has completely terminated. Now after seeing this, I will go on to check the coefficients of the these continued fraction expansion, and they all must be positive. Over here I have s raised to s by 4, which is a positive coefficient. I have 2s, which is again a positive coefficient. Over here I have s, which is again a positive coefficient. Over here I have 2 by 3s, which is again a positive coefficient. So all the coefficients are now positive, and I can say that this given polynomial, that is QSS, is Hurwitz. Now I will try to prove P1s to be Hurwitz, and which was 4s square plus 2s plus 1. I do not have space here, so let us move on to the next sheet. Now we will check whether this is Hurwitz polynomial or not. To do so, we will separate the even and odd parts. The even part over here is 4s square plus 1, and the odd part is 2s only. Now that means I will perform ms divided by ns. So considering 2s as the divisor, I will consider 4s square plus 1 to be the dividend, and I will continue my continued fraction expansion with this. I need 4s square, I have 2s, so I will multiply it with 2s again to get 4s square here, changing the sign, plus 0 minus. So these two will cancel out. I will get 1 as the remainder. Now this 1 will become the new divisor, and the old divisor will become the new dividend. So I will write 2s here. I will continue the division here. I need 2s, so I will multiply this with 2s. I will get it here 2s, and I'll get 0 as the remainder. That is after the sign change. I'll get 0 as the remainder. I need to check whether this continued fraction expansion is completely terminated or abruptly terminated. Over here the highest degree is 2, and I will see this is the first division, this is the second division. That means the continued fraction expansion has been completely terminated. Now I will check the quotients. The quotient over here is positive, also the coefficient here is positive, so I can comment now that the given polynomial is also a Hurwitz polynomial. Now if these two, that is P1s is Hurwitz and QS is also Hurwitz, so their product will also be a Hurwitz polynomial using the condition number 3. Not 3, the condition number 4. That means now I will write that PS is a Hurwitz polynomial. So that's it for this lecture. I hope you learned something new from this lecture. I want to comment one more, that this question is very important. It has appeared several times in the university exams. So I would request you all to go through it once more, have a practice over it, and then be confident about this. I'm giving you 3 numericals as a homework to check whether the given polynomials are Hurwitz or not. The solutions are need to be uploaded on the Compol. Now you will mention your name in the comment section below to mark your attendance. Thank you so much for listening to this lecture.